That's sort of said. Yes, so anyway, so these things have error correction codes. I'm sure if you guys have studied them in computer engineering, if you have engineering, but like, I don't know, it's like CRC codes or whatever. There's a much more, can get, when you're much more sophisticated, right? But when you're designing a chip, right, when you're designing a chip, remember, you're trying to make it as small as possible. You're trying to cram as many functions as you can in there. So typically, you do not have error correction inside a digital chip. So you're adding two 16-bit numbers together. You're adding multiplying two 16-bit numbers together, whatever. Your bit error rate has to be like, I don't know, how often are you okay for your computer to go AWOL? Like never, right? You just sit there. I mean, sometimes it happens and people get very unhappy with that, right? The thing crashes. Well, guess what? If you had 10 to the minus 9-bit error rate, every billion bits, you could get an error, and you've got a gigahertz clock in your microprocessor, and I don't know, millions of gates doing functions there. Basically, you'd crash every few seconds, right, before you're ready to restart. So basically, this says that so I don't want to give you guys the wrong message, because binary systems, digital systems are much more resilient to noise than analog systems, but also you cannot afford any errors. Like you can in analog systems, if you add to, like if you had I work in video, I guess you can think of video image sensors. If you got noise, we do analog all the time. We have A to D converters. You get noise, what happens is your image kind of looks like it's, you guys seen noisy images, like in the dark, right? It's not like your head turns into a red or pumpkin or something. Like that's what happens when there's a digital error. You just get completely mangled, okay? So this is one kind of error. So already this gives you some limit on the lowest voltage you can live with, okay? Now, it turns out that in my humble opinion, so in digital systems, this isn't even the primary issue, okay? So this is where I want to talk about digital noise. By the way, is this, so again, I'm like off in the desert here talking. Is this interesting? Are you guys like, does it make sense? Fits in? Okay, am I making sense? What's that?
It was way better than a PowerPoint presentation.
Okay, good. But digital noise, what do I mean by digital? I call it digital noise, it's really system noise. Okay, so this thermal, like I was very careful to tell you guys, hey, no clocks running in your system, like nothing else is going on. You just got your resistor, you're in the lab looking at it, you're in a Faraday cage. You were bad and they threw you in the Faraday cage, just kidding. But like you're magnetically sealed, you still get that noise, right? But now imagine if you have your 20 billion transistor circuit, it's getting clocked at 5 gigahertz. There's cell phones all around you. There's the power supply itself off the wall. There's you and your 10 million of your closest friends are on that same power network, and people are turning stuff in and out. Refrigerator next door is going on and off. All this are show up as glitches in your power supplies and in your grounds typically. Okay? So if you guys dare, next time you're working with a board on your microprocessor or FPGA or something, take a oscilloscope probe and probe your whatever supply is sitting there. Okay? Whatever supply is, I don't know. You guys worked with Xilinx FPGAs? You won't be able to go to sleep ever again. All right? So if you probe your 1.2 volt thing, it'll look like, it'll be 1.2 volt. It'll be like doing this, except it ain't microvolts we're talking about. It's hundreds of millivolts of glitches on power and ground. You really wonder I kid you not, this really bothered me when I started looking at this stuff. Is you're going like, how the hell is anything working? Because you got a 1 volt supply with like a couple of 100 millivolts of glitching noise going at like very high frequency. Okay, so that whole analog thing I told you, don't even bother worrying about that, right? This thing is what's gonna destroy you. And this does cause problems all the time, okay? And this, go ahead.
Is this because, like, of course, when we use like digital electronics, we're using like low voltage, therefore, like they're more susceptible to higher noise error?
Yeah, so the lower the voltage you are, it's, this is the thing. It's like a chicken and egg thing, but it's very correct. But there is your worst enemy sort of is yourself when you're a digital chip, because you're the one that's turning on and off, and you're the one that's being confused by other blocks in you turning on and off, right? So it does help that the lower voltage you are, typically tend to create less noise, but it doesn't make up for the fact that the lower the voltage you have, the more susceptible you are to making a mistake. Okay? By the way, the fourth noise, which I'm going to get into later, is, we're talking about frequency domain noise. You can think about that as zero frequency noise, is noise in your manufacturing process, which is one way of looking at noise. That's the way analog designers look at noise, but I'll get back to that. So that's sort of the third noise, but it's basically like unwanted stuff happening. Okay, so now that was a really long story about going back to I like long stories, as you guys can tell, is noise margin, which is this function of your digital logic family. Okay, what does it mean? It means generally, it means that if this was time and this was voltage, okay, like you have some threshold. Generally, your logic, to some extent, is going to assume that stuff like this is going to be like a 1, quote unquote. Stuff below here, a good logic family would decide this, would be a 0. Okay? And so you will do your best to stay up here. Whoops. And down here. You will do your best to do that. But let's say you got a glitchy system or something like that. Sometimes something unfortunate happens here and there, or you get some of this thermal noise. Like you might, if it gets bad enough, a 0 will turn into a 1. Like remember, this is time, this is voltage. Something happens bad enough, but the further this distance is from 0 to your threshold point, from 1 to your threshold point, the more noise margin you have, the more you can filter out this unwanted noise. Why does it? Because both, remember, you have 2 states. You have 0 state and a 1 state. They're both legitimate states. So they both need to be not susceptible to noise. You don't want to mistake a 0 for a 1 or vice versa. So they both need noise margin. So as you guys can just sort of, I don't know, I wouldn't know how to prove it to you guys, but the ideal situation is what? When your 0 and 1 are as separated as possible in terms of voltage, okay? And that your threshold is right in the middle. Why the threshold right in the middle? Because you are dividing your noise margin. You're equally as nice to your 0s as to your 1s. You could push it one way or another, but then you might, your 0s might, I could make this threshold down here, and we'll see how you can do that. Right, so this is like a 1, but then my 0, there's not, if there's much noise on the 0, you could see a 1 and vice versa, right? So ideally, you'd like to be right in the middle, okay? So if I redraw this, so that was in terms of time. So now let's think about it in terms of an inverter. and an inverter running in the voltage domain. So this is V in, V out. So an ideal transfer function would look like this. So first of all, let me tell you how this looks like, okay? So this is an inverter. So an input, a zero input is 0 volts. Okay, so this is the input axis. So I'm sitting here giving it a 0. And because it's an inverter, on the output axis, I'm going to get a high voltage inverter, right? Okay, so you're going to have this over here. Here, you're giving it a high voltage on the input. So for our case, this would be 1 volt. 1 volt. Again, input, output. Okay, so this is what the transfer function looks like. You guys with me? Okay. So what you would like to do is then put this guy at 0.5 volts. Okay, so this is the next thing before I, gonna sort of pause here pretty soon, and then we'll talk about your presentations and stuff. But this is the next thing that's really nice about CMOS logic family. Again, now we only have that to pick from, so we don't know how bad things were before. But one, because of this pull-down, pull-up network, when you are passing a 1 or a high supply through, after you charge your capacitor up, there is no resistive dividers, right? So let's say your PMOS is on. Let's think about the inverter. PMOS is on, NMOS is off. Got my capacitor, VDD. This guy is in the input. So let's say this is the situation, right? After you charge this capacitor up, it's going to go up, this value is going to go up to VDD. Okay? It's not going to go to 90% of VDD. It's not going to go up to 80% of VDD. It's going to go up to VDD. Okay? If I had a resistor here, then I would have to do a voltage divider between the value of this resistor and the resistance of this transistor. Okay? And this would be at some some value. I don't know what, right? Depends on what this value is, depending on what this value is. But as you guys saw, hopefully, or will see in your projects, okay, if you're not worrying about timing, you guys weren't picking the size of your transistors, or you'll see, you don't have to pick the size of your transistors. Your output, if you give it enough time, it will always go to VDD. Because this guy's off. Again, if this guy was on somehow, even a little bit, this NMOS, again, you'd get a voltage divider action, and you wouldn't go all the way up to the supply. Okay, and vice versa. If the PMOS didn't turn off and the NMOS was trying to drive that guy to ground, it wouldn't go all the way, output wouldn't go all the way to ground. You'd get some voltage divider action. So in a CMOS circuit, one of the nice things is you can use the entire supply voltage that you have. If you have a 1 volt supply, your 1 without a noise is sitting at 1 volt, and your 0 is sitting at 0 volts. It's not like the older logic families, a 1 would be 800 millivolts, and a 0 would be 200 millivolts, just because they didn't run like this. They didn't have a situation where you could turn part of the circuit completely off, and your loads would end up being resistive and not fully capacitive. Okay? So again, in an NMOS logic family, because we have PMOS network on top, NMOS network on bottom, and they're never on at the same time. Okay, it's guaranteed again, once you settle, they're never on at the same time. And you're always driving the gate of MOS transistors, which are capacitive. You're always using your full power supply, which is really nice you're just utilizing it. Again, remember, the other thing to remember is power is equal to V times I. So I want to keep that voltage as low as possible, but no lower. And if I'm using it, it's costing me power, so I want to use all of it. I don't want to throw away any of it. Okay? So, and then the other thing that the CMOS logic family does is it's very easy to tune the location of this crossover point. Very easy, easier than other logic families, not completely easy. And you guys will talk about how you can, basically what you do is you can size your NMOS and PMOS relative sizes, and you can adjust this. So what a CMOS, a real CMOS inverter looks like, is it kind of looks like this. Which isn't perfect, because again, like as you, at some point here, you're at these intermediate voltages on your input, which is not where you would normally be, but it's stuff that happens in transient where like both N and PMOS are momentarily on, so you get these kind of intermediate values on your output, but you don't want to be sitting around there. You want to be, remember, this is your input axis. You either want to be here or here. So this is your input low, input high. You want to be kind of away from this point, this central area, which is like the death zone. The digital death zone. Is actually the reason I mentioned that is because we try to use that in analog domain. It's like a nice poor man's amplifier. But you want to stay away from that. But you can make that transition point, you can make this region very small, very narrow. So again, you don't lose your noise margin. Okay? So, again, long story short, reason number 2 for CMOS being good and popular is your noise margin. Your rejection of your noise is very good, okay, in CMOS because of these factors, okay? Use the full power supply. You can set your threshold value relatively easy, okay? And so you can optimize your noise margin, okay? So that comes into the reliability.
Can you repeat the first reason?
Yeah, it's that you can use your full power supply. So if you have a 1 volt power supply, your binary 1 can be 1 volt, and your binary 0 can be 0 volts. Again, you guys don't have anything to compare to, so you got to take my word for it, but alternative logic families did not have that. So if you do TTL, have you guys even heard of TTL? Hope you haven't. Who has? I hope. What's that?
The acronyms for transition is the logic, but I don't know what specifically was.
Okay, good. Make it stay that way, man. You don't want to know. Like you'd have like 3.3 volt supply and your high would be 2.4 volts or something. Okay, because you've got a bipolar transistor and there's a base emitter voltage drop and blah, 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 blah. Okay, no good. So this is why reason number 2 that CMOS won is noise margin. And it's, again, the 4 quadrants: performance, power, cost, reliability. This is one aspect of reliability. You do not want zeros to get confused for ones and ones to get confused for zeros. Okay, yeah. What's your name?
Gabriel.
Gabriel.
So, what's the trade-off for like reliability? Like we're talking about, like we have the ideal model right there, and you showed us like what the actual one, and I know you said we can make it better. Are we going to be talking about like the trade-offs in order to make that better? Like, does that mean the cost goes up in a sense, or?
See, you're forcing me into long-winded answers, man. Well, what happens is you don't really, you don't have a lot of, the only thing you really have control over, in some sense, is the location where this crossover point happens. You can make this sharper, and we do, for analog design, because this to us, when you're using this for gain, so this is like digital, analog. This looks like gain, which is sort of bad in a digital circuit, but good for analog circuits. So we'd make these sharp, but we do that at the expense of speed. And you almost would never do that in a CMOS circuit. So in that sense, you don't have control over it. In some sense, you can do better if you use older processes. these, not only as we'll see, or as you guys will see in the slides and so on, that a lot of what causes this stuff, some of it is just the nature of both N and PMOS being on, but some of it ends up being second, third order effects with aggressive process technologies. As your transistors are you familiar with NMOS transistors? Like the square law model, saturation, linear mode, and all that stuff. So they don't really act like that at 45 nanometers. There's always second order effects where your saturation isn't square law dependent, all sorts of unfortunate stuff happens. So the more aggressive the processes you take, the more and more gnarly this starts looking, but you accept that to go, pack more stuff in. Yeah. Does that sort of answer your question? Yeah. By the way, that's in this whole thing about supply voltages is another reason why, and we'll talk about some other stuff. Part of the reason why power supplies are stuck at about 1 volt or 0.9 volts. For a while, you were getting from 3.3 volts, we went to 2.5 volts, went to 1.8 volts, 1.3 volts, but generation after generation of processes right now, like a 45 nanometer process, the supply is 1 volt. 28 nanometers process supplies 1 volt. 5 nanometer process, I think their supply is at 0.7 or 0.9, but it hasn't gone down to 100 millivolts or something. You just can't drop it. And there's an enormous pressure to drop that supply voltage because it means power consumption. Okay, and it means other things too, but they're sort of stuck there because of noise margin reasons. Okay, guys. So any questions about that stuff? And then if you go again into the slides, I'm not getting to the minutia here of there's definite mathematical definition of noise margin in terms of the relationship between input and output and all that stuff. That's for your amusement or study. Maybe I'll ask you guys in a project to give me the actual noise margin on the circuit, and you can go look it up there, but I'm not like covering specifically those. I'm trying to get you guys the basic concepts. Go ahead. What's your name, sorry?
I'm Brianna.
Brianna, nice to meet you.
Nice to meet you. Which slide deck is this information covered in?
I think it's still in that 3, is that level? Which one was the last one I asked you guys to read from last week? 4, okay, so we're still stuck in that 4.
Okay,
Yeah,
thank you, Professor.
sure. All right, guys, if you don't have any questions, take a break till 2:30, and then we'll pop back, and then we're gonna look at some volunteers. I keep forgetting the name of this thing they have in the military. It's called, it's a mix between volunteering and being ordered to do something.
Volunteer?
What's that?
Volunteer?
Volunteer, or there's something else. Voluntold, thank you. Voluntold. So either volunteer or you'd be voluntold.
George, man. And then how was the data that I put for you? I didn't put the whole thing. Oh, but you did partial part. Yeah. You guys have been on a prospect. I can see that's like a lot. No. Yeah, we could just say or cost 10, 6 power. And I said, this is yeah, but no, but like, it's not accessible. It's like $25.
So I sent you an email earlier this week about the very first presentation I did. Like, I submitted it like this week. Is that okay? Or,
I mean, think of the presentation right now. Yeah, what I'd like to do is have you guys think of it as like real work. When that happens is you're just, it's like a living document. So I'm not looking for you guys to clean it up.
Oh, just to make sure like we're on.
So if you're sending it late, if it hasn't happened, it might be like you might have less than
Yeah.
so the end point was at the point.
Yes, exactly. Pretty much just.
What's that?
Me and Ethan want to go first for the polling.
Okay, cool. What do you guys, what do you
We picked the Arduino Mini.
We picked up, we have a breakdown of prices. The problem that we have, we made it, and it's more expensive than the retail price. And so
We're calculating the parts of the Arduino, because you have to do that. It's like super close to the retail price. Like just
there's no secret Yeah.
Okay, it'll be interesting to see what you guys come up with. I think if you do an honest job of it, we'll see that across the board. Like there's a reason why products, whatever product was not difficult to compete with, would be replaced by products. It's the nature of the beast. So if we did an honest job of it, so then you start going, wow,
you were saying how previously the
that's still gonna be CMOS.
Yeah.
So what happens is, what happens is, multiple power sources. So the lowest one is called the core. So that's driving all the logic inside. So like 4.99 billion then for historical reasons, because the power supply started as pretty much so historically, a lot special devices. Just so that so that's usually where you
Is that, Yeah, so pretty much, this is pretty much kind of like doing like in real life, right? You have this component, there's like 20 volts, you have this laptop that's like 12 volts, right? And you're literally just like using electricity from like 110 volts, right? You kind of just start kind of adding adapters and kind of like adapting the electricity based on the capacitor. Which is pretty much what we're doing with that small circuit. When you're talking about chips, like, how much is the profit? Say that it's for like